Radii of a slightly tapered cylindrical wire of length L at its ends are A and B. It is stressed by two forces, each of magnitude F, applied at its ends. The forces are uniformly distributed over the end faces. If Young's modulus of the material of wire is denoted by Y, extension produced is. Okay, so there is a wire which is tapering. It means its radius is changing continuously, and it is changing linearly from A to B, like this, from A to B, and it's given in the question that its length is L, and I am considering a general radius R at a distance x from one end, and there is a force acting on the two faces, end faces, and these forces are uniformly distributed as it's given in the question. Now we have to find the elongation in this rod. So for that we're going to find stress at a general section having radius R as shown, and for that we have to first find R, the expression of R, and for that consider this figure. So since radius is changing from A to B linearly as shown in the second figure, so the radius here is A while that here is B. At a general distance x from one end we have considered the radius as R, and it is changing linearly. So consider this triangle formed here like this, on which I am sliding my pen. So this triangle, so it has two triangles in it, two similar triangles in it. One is this, the larger one, and the smaller one, the yellow one. So these two are similar triangles. So using the property of similar triangles, we have this expression A minus B, the ratio of distance. So A minus B over L is equal to R minus B over X. This is obvious. This total distance is R while this distance is B. So this small distance here in the triangle is R minus B. Similarly here it is A minus B. Okay, so from this we get the expression for R. Now the stress at section R, at this section having radius R, is force divided by area. So area is pi R square. So since the stress is changing with R, or you can say with X, so it's not a constant thing. Only when we have stress, same stress at two sections, then only we can find strain between those two sections. So here stress is changing. So what we can best do, we can assume a very small, we can take a very small distance dx, and on these sections we can approximately assume that the stress is same. Okay, so stress at section that is at distance x is force over pi r square, and assuming the same stress at these two sections, the distance between these two sections, that is dx, it will change, and change in dx over dx, this is a strain. Strain is a stress over Young's modulus. This is the formula we know. So to find the total change in length, we have to integrate this change in dx. So what we have to do, bring this dx on this other side and integrate these two. So total change in x is integration of this quantity. And to integrate this, since it is having two variables in it, r and x, we have to bring these two variables in a single variable form. So for this, either we have to replace r in terms of x or x in terms of r. So we have this expression of r. So differentiate this. We have dr is, b is a constant. So dr is a minus b over l dx. So okay, we are going to replace this dx in the integral here. So I'm going to replace this dx by this expression. So it will be equal to dr upon this, and since it is now in terms of r, we have to put limits of r, and radius is changing from b to a here. So the change in radius is from b to a, so it is now limits of r, since it is dr here. So whatever comes after d, the limit has to be put of that quantity. Okay, and then we have to solve it. So we are getting this expression, which is the total extension in the rod, FL over AB pi. What else we could have done, since it is an objective question? We can rule out the three incorrect options. Like if you see the options here, if it was, if A and B was same, suppose it is a regular wire of uniform cross-sectional area having same area throughout, then if A and B was same, then we could have used the direct formula. Strain is stress at any section which is now which is uniform everywhere. So stress, that is F over pi r square, and in that case the formula would become like this. I'm just writing it. If we had A and B as same, suppose we had this type of wire having same cross-sectional area, same radius A here, A and B are same. In that case, stress is at any section F over pi a square. And if we divide this stress by Young's modulus, so this is strain into original length. So this is delta L. So if A and B they become equal, then in that case delta L will be of this value. So only that option will be correct, in which if we put A and B equal, we get this expression. So if we check, put A equal to B here, and you check, so this expression is similar to this. So this option 1 can be correct. Option B, if we put A and B are equal, so we have 2A square. So there will be a factor of 2 downstairs, while there is no 2 here. So this will give a wrong result. In case A and B are equal, this will be indeterminate or infinite. So this is a wrong result. If A and B are equal, this matches with this result. Okay, so these two are possible. A and D are possible. Now, how to decide whether which of these two, A and D, which of these two can be ruled out by some logic? See, if we have B equal to 0, suppose we have B equal to 0, that is, if suppose this tapers like this and the radius B is 0. In that case, stress here will be force upon area, and area is 0 or almost 0. So stress here will be infinite because area goes to 0 here. In that case, if stress any section at any section becomes infinite, strain here will be infinite. In that case, strain would be infinite, and therefore the change in length of this rod will be, this wire will be infinite strain. So if B becomes 0, we should get infinite strain. In this A option, if B is 0, this is not giving infinite result. In D option, if we put B tends to 0, then this goes to infinity. So option D is correct. So this is how we can rule out these three options, and we could arrive at the correct result, option D. Okay, thank you.